So we will kind of pick up. What should I hit? Yes. So pick up where we left off. I'll try to remember where we left off. My two sections are a little bit off now, but it should be okay. Because today, Thursday, next Tuesday, we're just going to be rehashing, kind of looking at different examples of the same topics we've been talking about, kind of getting us ready for the exam, which is next Thursday. Right. So I've got that practice exam up there. I don't know if we'll have time to dive into it at the end of today's class. We might have a little bit of time. If not, we'll definitely probably pick up with that on Thursday. Today we'll kind of look at how we do a lot of this in Stata. So we got through all the slides last week. I believe we kind of looked through this STAR public use. We're kind of looking at some of this Indiana kind of data. I don't believe we had started to look at this kind of powerlifting data set, or we had just started. Is that sounding familiar?
I think we had just started.
I think we had just started. That's what I thought. So I just wanted to, I believe that's what it was, but I wanted to make sure my brain is working. I've had quite a weekend. I got sick Friday. You guys don't care, but I then had a cat that was supposed to get spayed 3 weeks ago. I went to go get it spayed and found out I was pregnant. So it gave birth this weekend. So that was fun. So if you don't know, when cats give birth, first of all, I think this was like a bad cat because like she wouldn't clean. So I had to like cut the sacks of a couple of the kittens so they could breathe. It was a whole thing. Right. So that's where I'm coming at this week from. So I'll try to have, a lot of energy. I will try to be good, but it was an exhausting weekend. So we'll start out opening this powerlifting data set and thinking about a lot of different topics we were talking about with multiple linear regression. And I'll try to touch on some older topics as well. Also a common mistake that I saw in problem set 2. So let's see here. So I'm going to generate this kind of category. So there's really 3, and I might have mentioned this last week, but just starting off in the same place. There's 3 different types of these powerlifting meets, right? So one is they call raw. It's just there's no assistive equipment. Wraps, there's a minor assistive equipment, and then this multiply, which is like excessive assistive equipment. So any one of these meets has to be one of these 3 categories, right? So we're starting to think about, we might have some concerns of what? If I've got 3 dummy variables, it can only ever be one of those 3. It can't be in 2 at the same time. What could I have? This term was said sometimes it's perfect. Sometimes we have imperfect multicollinearity. So these 3 variables together will have some collinearity if we try to include them all at the same time. But we're not doing that yet. So I don't know if we talked through this, but it's kind of worth thinking about. In fact, because I have the male one in the data set here, let's think about a different variable where we could sign the bias, right? So you have this do file, you can kind of go review, okay, what if I ran a naive regression? I didn't include the dummy variable of male. I think that might have been the one that we did kind of talk through last class. Let's think about a different one where, so I'll call this bias example number 2. So let's say I'm trying to predict the total weight lifted in these powerlifting meets by the person's body weight. Right? And then I also have this omitted variable of age. So I'm going to run this very naive regression. I end up seeing that the effect of 1 more kilogram of body weight predicts that the amount of weight they can lift goes up by 5.2 kilograms. Right? That's how we interpret those slope coefficients. Okay. If I'd left out this important omitted variable of age, this is where we can start to think about what would the bias be that existed. So excuse me. So the slope coefficient estimate we were seeing contained the true estimate plus what the effect of the omitted variable would have been if I had included it in my regression. So if we're thinking about here, the regression we ran simply looked like this. Okay. Let's say there was this important omitted variable, which was age. Right? So my bias would have been the effect of age times the covariance of that variable I left out with the variable I included, or I'm looking at the slope coefficient of, divided by the variance of that variable I'm looking at the slope coefficient of. Okay. So this was the bias that was existing in our estimate because we didn't include this important omitted variable of age. Now, if I had included age, what do you think the effect would have been? Right? This one's kind of tough. You can probably tell a story that goes either way. But as you get older, generally what happens to your body? You guys haven't felt these effects yet. It deteriorates, right? So I can't do what I used to be able to do when I was 21, right? So as age goes up, what's probably happening to the weight that these, you could lift, we were holding everything else constant, this is likely going to have a negative effect, right? Or beta 2 here, we would expect less than 0. What do you think the covariance would be between age and your body weight? So as you get older, once again, you probably haven't experienced this, it gets harder to stay small, right? So as you get older, what's likely happening to body weight? You think it's probably positive effect. Now here it gets weird because the nuance of whatever example you're looking at, maybe our intuition isn't right here. But if I was to ask you a question on the exam and leave it open-ended about what you think the sign of the bias, as long as you explain to me why you believe beta 2 is what it is and correctly identify what beta 2 represents, which is what the effect of that important omitted variable would have been on the y variable if you include it in your regression. And as long as you correctly describe the covariance as being that correlation between age, the variable that you excluded or omitted, and the variable you included body weight, I'll grade it accordingly, right? So we think that our bias here is, and I didn't mention one thing, it should be complete. What's the sign of our variance always? Always positive. So my bias here is what? Negative times a positive divided by a positive. I'm going to see a coefficient estimate that's actually a little bit too small, right? It's going to be lower than what the actual effect would be. If I include this important omitted variable, then the estimate I see just becomes what the true estimate should be. So let's take a look at this, right? Maybe, there we go. So I've got that variable of age in my data set. So I'm going to select it, maybe. Okay, there we go. So if I run this regression, so it looks like my coefficient estimate was actually a little bit too low before, or it had a negative bias in it, right? Now it wasn't huge, the size wasn't large, but it was a negative bias, right? And so sure enough, what was the effect of age when we included it? Negative, right? We can also use that correlate command, say what was the correlation between body weight and age, and tell it we want to see the covariance. Sure enough, that covariance between age and body weight lifted, right, was actually, sorry, age not body weight lifted. Age and body weight, right, was positive, right? The older the individuals got here, we saw that they kind of tended to be heavier. Okay? So our intuition kind of led us correctly that we had a negative bias existing when we exclude this important omitted variable. Okay? So I can guarantee you on the exam, I will have one, if not multiple questions related to omitted variable bias, right? Probably one where I'm asking you to do something like this, where I'm talking about the size, or sorry, the sign, and a second one where I ask you about the size. Now, let's say on exam, I gave you this output here. So you have the important omitted variable included, and I then gave you this correlation matrix. And I said, let's assume you ran a naive regression where you only included body weight. What would the size of the bias be? Well, what are the things that we need? We need the coefficient of age. If we did include it, well, I gave you that output, so we can grab that. I gave you the covariance. We can actually see where we can also get the variance from that output. Then just be a matter of plugging those three values in. Right? So for us, what was the effective age when we included it? About negative 2.05. What was our covariance between the two variables? 18.85. And then these cross kind of values here, well, the covariance of a variable itself actually ends up just being the variance. And we could walk through the mathematical proof for it, but we've talked about it before and why. We know this is just going to represent our variance. So we need the variance of the variable included in our naive regression. We excluded age, so we need the variance of body weight, right? So we would take what? Negative, I think it was 0.205. Is that what it was? Yeah, 0.205. Covariance was 18.85. And then divided by the variance of variable included, so 524.4, right? If we do that, someone can beat me to it. You can tell me what that is. Otherwise, well, maybe I'll get it entered into Excel here. So negative 0.07 should have been the negative bias that was existing. Well, sure enough, if I did have the naive regression, how much lower was the estimate I was seeing? Should have been 5.27. I was seeing 5.2. What was the size of the bias? That same value we just found of negative. Whoops, I forgot my negative sign. Negative 0.07. So there I could give you output and you could calculate the size of the bias. Right? Any questions on that before we keep? So these next few classes are really meant for you guys. I don't have a ton prepared in terms of like I got materials and I have things I can do off the top of my head. But you know, ask as many questions as you want. This is to kind of get you prepared for that exam. So do not hesitate to stop me. What if this changed? What if we did that? Anything. Even if it seems like a dumb question, we're going back. We're going to go back to some very basic stuff today as well. So no topic questions off limits. Okay. Yeah.
Oh, will you repost this after class 12 edits?
These edits?
Yeah.
I can save this and then try to repost it. Yeah.
Okay.
Yep. Back. Yeah. So I can kind of do that here. Yep. Back. So I don't forget by the end of class. What's today? 10/8 edits. Save them. And I'll save them along the way, not just right there. Okay. So where was a topic that we kind of more left off on? I went back to revisit this omitted variable bias. One thing that I saw people do on the problem set that I just want to bring up before we kind of dive back into joint significance is related to heteroscedastic errors, right? So let's say we just run a very simple regression, right? I'm going to regress total weight lifted on body weight, right? I can get some output here, but I'm concerned with that my errors might be heteroscedastic, right? So anytime I ask you to do something in a problem set, I've said this before, where should you be able to find how to do that? In one of the do files we've used in class, right? So when I'm asking you to test for heteroscedasticity, the test that we did, let me see if I can remember the syntax, is just this SStat IM test, right? So you'll notice when I run this, it gives me multiple things. One of them is the test for heteroscedasticity. Now we didn't really focus on it too much because we weren't calculating it by hand, but these are essentially test statistics. And then these are essentially your corresponding p-values. I said as far as I'm going to push you is just knowing how to take that p-value and make a rejection decision. What do we start out assuming? Errors are homoscedastic. If we can reject that, we're saying that there's evidence they're heteroscedastic. So some of you, I'm guessing I'm probably speaking to the wrong crowd, because I would assume it's people that maybe weren't in class when we went through this or haven't been following along, did some Googling. Let's see, I think it's just the HT. I think it's all that wrong. Let's see. Yeah. So you did some Googling, how do I test for heteroscedasticity? And Google tells you this, or maybe how do you do it in Stata? Google tells you to run this HET test command. This is not doing the same thing as the IM test command, right? In fact, if you kind of look at it, like here, it's kind of attributing the people that came up with this test, right? Down here, it's mentioning these two, but also these two. In fact, it doesn't mention a third. I think it actually runs this one as well. But what this output is giving you, because honestly, I haven't really used this command. I'm sure I use it at some point in my life, but I haven't used it in forever. What it's doing is doing multiple tests for heteroscedasticity and giving you kind of like the average across all of them. That might sound good in theory, but different tests for heteroscedasticity are going to be more accurate for different scenarios. So when we're starting out with a very simple linear regression, the one that's going to be the most accurate is not these two. It's actually going to be this test for heteroscedasticity, right? These can do some things that we account when we start to include more variables in our regression. But we didn't talk about that, right? We were just talking about testing for heteroscedasticity in a very simple linear regression. So what you'll notice is this test statistic. So we didn't even talk about the chi-square distribution, right? But where that test statistic is testing for heteroscedasticity and the corresponding p-value. Now here the p-values are both 0, so it's okay. It didn't matter which one I used, right? So I've got 5,900 and then 5,000 up here. But leaving the problem set, it's a much smaller sample size. And what ended up happening is if you use the command you're supposed to, that we've been using in class, that IMTest, you would have, I think, rejected. And then if you use the other HET test, you actually failed to reject, right? Because it's giving you dramatic, I mean, here, our test statistic, the difference is 900, right? So we can get very different p-values as well, and that might influence our rejection decision. So anything you use for these problem sets should be somewhere in these do files, right? And there's probably other ways of doing it, and if you do it correctly, that's fine, but you might look this up and not realize these aren't exactly the same tests. And in fact, this is multiple tests and kind of averaging out across 3 of them, okay? Okay, so I not to, but when I grade, so I've told my GAs when they originally go through it, they might skip this on yours if you use the HE test. I'm feeling nice, and so I will grade it after the fact, kind of according to what result it gave you. Kind of the template that I gave them was based off of using the command that we used in class, and so they started to see this pop up and let me know, like, well, do I mark all these wrong? Well, probably should have used this one, but technically this is one way to test for heteroscedasticity. So I'll go back through after they get through grading, and I'll kind of grade this according to what that test would have given you, right? But moving forward, try on these problem sets only be using the commands that we use in class. That's all you should need, okay? Because if you Google stuff, it's kind of confusing, right? You're not, well, maybe I shouldn't make this assumption, but most of you probably aren't experts at this yet. And so even though you think it might be doing the same thing, there's a lot of black box going on here. It might not be doing exactly what you think, okay? All right. Anyways, so now we'll jump back into what we kind of left off with on Thursday, which was joint significance, right? So we've got this data set. I can run this regression, and I'm going to run, actually, I'm going to run, skip down here. Here's my basic regression. So we can run 2 models, one where I've included only body weight and male, one where I've included those, but also the age, and then this was the kind of category of lift was in this raw category, no assistive equipment. Okay? So I can kind of see my results here from the 2 regressions. Try to get them all on the same screen, at least somewhat. Excuse me. So in practice, you don't have to run the restricted model. So here's where we want to be careful. What's our restricted and unrestricted? Because I think it's getting confusing for some people. Our unrestricted model, and this is a less technical way of remembering it, it's the model that has more variables in it, right? Our restricted model is the one where we were kind of starting out naive. We didn't include all the variables that we had in our data set. So here, our original one that we only had body weight and male, this is going to be our restricted model. So the R squared there is 0.65. What should happen to my R squared if I add in more variables in that unrestricted regression? R squared should go up. It can only go up. In fact, there's no possible way it can go down. Theoretically, it could stay the same, but even then, it's probably going to be infinitesimal change there, right? So what we started then to talk about was we want to determine whether these variables that we added into this unrestricted model, do they have what we call joint significance? Another way I've said thinking about this is, do they increase the proportion of variation we can explain in that y variable at a statistically significant level? So if we want to test statistical, if we have statistical significance of something, what do I need? So if I asked you if something was statistically significant for a slope coefficient, what do you use? You compare the test statistic or to the critical value or your p-value to alpha. So we're going to need a test statistic. So before, when we only had one slope coefficient, we were just taking the estimate that we saw and then dividing that by our standard error. Now we'll look at this later on. This is our formula sheet. But another way of thinking about this standard error, we said it's kind of like the standard deviation of our slope coefficient. And the actual equation is, let's see if I can remember this. So it's the actual y minus the predicted y squared over n minus 2, right? This will become important in a second. So we talked about this n minus 2, just like when we go all the way back to a sample mean, n minus 1 was telling us our degrees of freedom for which student t distribution we should be using. We're now going to calculate a test statistic, but we're not interested in the slope coefficient. When we said we were testing joint significance, we were interested in, can we explain more of the variation and why? So the sample statistic we're now interested in is the difference between our unrestricted models r squared and our restricted models r squared. You can almost think about this as the actual sample statistic we were interested in was like the change in our r squared. That was the actual statistic we wanted to do a hypothesis test for, testing this joint significance. Did adding these variables in change that r squared in a statistically significant way? Okay. Now, because we were then in our F statistical equation, we can go back to it, dividing by Q, which, what did this represent? Do we remember?
Number of extra or more dummy here, or
The number of variables, basic, less technical way of saying is the difference in the number of variables used in the restricted and unrestricted model. Or we said this was our number of restrictions. But yeah, basically, how many variables are we testing the joint significance of? Do we add in 2 more, 3, 4, 5, etc.? We then had in our denominator, and this is another place where people kind of made a pretty common mistake. We had 1 minus the r squared, but we're kind of thinking about what this change in the r squared was relative to kind of our new model. So here, this was the unrestricted r squared in our denominator. Okay? So it's, in a way, you can kind of see it's like the proportion of the change in r squared relative to, it's not what our model explains, but it's actually 1 minus, so the proportion of what we can explain. And then we scaled this, dividing by n minus k minus 1, right? Where k was what? The number of variables. And once again, this should match up with the unrestricted model. So it's the number of variables in our unrestricted model. And then n is always our sample size. It's the same kind of thing. Okay? So this wasn't a t, doesn't come from a t distribution. It came from what? F distribution, right? We had a test statistic, but it was coming from this F distribution, which when we kind of looked at it visually, it just had this long right tail. Okay. Any questions on anything here before we keep moving? Okay. So we can go back and look at that output. I can get the r squared from the output. I can get the number of restrictions. Ours, I think we only added in 2 variables, right? The unrestricted model only had 4 total variables on the right-hand side, and we can look at what our sample size is. So we'll go back here. And what are those values? So it went from 0.6539 to 0.6939. So it went up by about point. Oh no, did I break it? Hold on. Let's see if we can switch this back. What is it that about? Let's see before I do the. Age-old fix for everything and just shut it down and open it back up. So I can kind of keep talking as we go. I don't think I bumped anything. So as we kind of wait for this to reload. So I've got that output from my restricted model. I can grab that r squared. I can then look at my unrestricted model, grab that r squared. We said the number of restrictions was 2, variables in that final regression k was 4. Then it's just a matter of plugging things in, right? So once we plug that in, we'll have this test statistic, right? We then can use that to find a p-value. Hopefully that's a good sign. And once we have that p-value, we compare to alpha and say, did we see that the R square increase, right? That it increased at a statistically significant level. Okay. So I can grab those two values, right, from my output. I can then look, oh, I've got 86,000 observations here. So I'm going to make a point about this here in a second. Right. I then have 4 variables, that's K. How many variables did I add in? 2. Basically, you can plug all of these in to my equation, right? And that should give me my F statistic. So I could use Excel, copy paste this, or I can just create a new variable, call it fstat. I mean, don't really like to do this in general because then you start having a bunch of variables that you don't really want to include in regressions, but at least we'll kind of give you what that value is pretty quickly, right? I did this a lot. I know it's probably not best practice, but it's very much easier. It's easier for me than switching back and forth between state and Excel or my calculator, right? Probably what's best practice if you do it this way, just so that you don't have things muddying up your data set, you should probably then drop it after you've gotten the value. But that's a little bit I'm getting into the weeds here a little bit. Now, excuse me. If you actually run the command that will do this test for you. So here, it's just test and those 2 variables that we included. So if you run the unrestricted model, and then you say, well, I want to test the joint significance of these 2 variables I added in, which were raw and age, you don't even have to run the unrestricted model. If you just do this, that's not what I want. It'll run it in the background for you, do the joint significant test, and give you that test statistic. So notice 5,637, we found 5,643. Why are we off there? I think we talked about this. When I'm doing it by hand, I'm rounding everything to the 4th decimal. Doesn't seem like it'd make that much of a difference. When we're dealing with large sample sizes like this, it can kind of create a pretty, a visible difference in between our test statistics. Okay. But it really doesn't matter that we rounded, right? Because this is a crazy high test statistic. So the actual critical values are going to be very different for the F distribution, which is why if I'm asking you any questions about joint significance or the F distribution, I'm just going to rely on the p-value, right? You'll either be given the p-value, right? We'll kind of make the decisions based off of that. Now I might ask you to calculate the test statistic, but I won't then ask you to use that test statistic to make rejection decisions. Although with really large sample sizes, these values we kind of default to when we looked at the F table, that last line. So we probably could come up with close approximations for the critical values, but I won't push you guys that far. Okay. So any questions on kind of this calculation before I change 2 things here? We're okay with this? Let me think about what order. I think I know what order I'm going to do this in. So we'll scroll down here. I'm going to use this code to generate some random numbers. And then basically I'm going to make a smaller sample size kind of in my data set, kind of behind the scenes. So I'm going to have this small sample variable that I've created, which basically is only going to be a 1. Well, I think I already sorted it. Yeah, so all of these are zeros, except for 100 of the observation I selected at random. Right? So I'm now going to run this same exact regression that I had up here, but I'm now going to do it for a smaller sample size. Okay? So now my sample size is only 100. Now notice, just because I took a smaller sample size, my R squared will change a little just because it is completely different samples, right? I might, if I were to take an infinite number of samples of the same size, I would always kind of find that same R squared. But if I take any 2 of those samples, they might be a little bit different, right? So here, a little bit different, but pretty close, right, from the smaller sample. Now, what do we notice has happened to the statistical significance of each individual slope coefficient here? Which of these could I say are statistically significant at the 5% level? Yeah, just body weight and male now. Before, which ones could I said were statistically significant? Everything was 0. All because when we have a larger sample size, what's happening to that standard error? it is,
Producing.
yeah, so if the denominator is larger, my standard error would be smaller. If I divide by a smaller value, my test statistic is larger, which leads to be more confident. You're all saying it, but you're drawing it out. Smaller p-values, right? Which means it's more likely that I can reject the null. Now that was with higher sample sizes. If we work in the exact opposite, smaller sample sizes would blow up my standard errors. Dividing by a larger number decreases my test statistic, making my p-values larger, and now I'm less likely to be able to reject the null. Now, just because I'm less likely doesn't mean I won't, right? So for body weight in male, notice the test statistics are a lot smaller, but the p-value is still 0. And I can still reject at that level. Now, for the other two, the p-values got high enough to where I can no longer reject. Okay? So higher sample sizes always makes it, even if you can't remember the mechanics, higher sample sizes, no matter what we're talking about, always makes it more likely you can reject. That's just like that, like I said, if you don't worry about what's going on in between, that's the start and the finish. Higher sample size, always going to be a little bit more likely we can reject. Okay. So if I didn't give you any of this output here, and I just asked you to make decisions based off the confidence intervals, why could you tell me that body weight and male were the only two that were statistically significant at the 5% level?
Not 0.
So what's not 0?
Intervals okay. 0.
The interval doesn't include 0. What's a less technical way of remembering this, even though it's kind of technical? Anytime I have a lower and upper bound that are the same sign, I can reject, right, at that level, because that tells me 0 is not in this interval. 0 can't be one of the possible true values. Anytime I have different signs on my lower and upper bound, that means that 0 is in that range and 0 could be one of the true values. So I would fail to reject for those. Okay. Questions on that? Like I said, I'm trying to hit old things along the way as we're moving through some of those. Yeah.
Can you repeat that again? You're saying you would reject the 5% interval level because 0.
So these two confidence intervals include the value of 0. They cross over.
Right.
So that's telling us 0 could be one of the true possible values for the slope coefficient on these variables. So if it could be one of the true values, I would fail to reject them, right? If it could be the true value, I shouldn't be rejecting it. I should be failing to reject.
Right.
So anytime you have different signs for your lower and upper bound, that's telling you 0 is going to then be in that confidence interval, could be one of the true values, I'm going to fail to reject. Anytime they're the same sign, that's telling you 0 is not in that interval, 0 can't be one of the possible true values. Well, if 0 can't be one of the possible true values, I definitely should be rejecting it. Yep.
That relates to p-value, and if it's less than it's like less than point.
So anytime your confidence interval doesn't include 0 here, what has to be true? Your p-value would have to be less than, this is the 95% level, so your p-value would have to be less than 0.05.
Yeah.
Sure enough, it is. Anytime it includes 0, your p-value must be greater. Sure enough, it is greater than 0.05. Yep. Any other questions on that before we go back to joint significance? This sets us up to think about it well, though, so this is good. Okay. So I've got this smaller sample size. We talked about its impact on our kind of joint or on our individual significance. What about its impact on our joint significance? Right. So if I'm thinking through this, if I've got a smaller sample size, we went from like 86,000 to 100. This is going to decrease my sample size here. What's that going to do to my denominator? Yeah, if I divide by a smaller number here, it's going to increase it. If this is now larger, what's happening to my F statistic? Dividing by a larger number, it's going to decrease it. What's this going to do to my p-value? Increase my p-value, right? Because I'm now having a smaller test statistic. That area in the tail is going to be larger. if I have a larger p-value, I'm going to be less likely to reject, right? So it's the exact same thing here. I did the opposite direction, right? I went with an increase in sample size, but it's the same thing. If I have larger sample sizes, easier to reject. Smaller sample sizes, more difficult or less likely I can reject. Okay? So if we go back to that data and I run the same test for joint significance, what should be happening with that smaller sample size? My F statistic should be, and the p-value it tells me should be larger. Let's see if I'm full of it. All right. So we run that test command in the same two variables. Sure enough, I mean, our test statistic before was like in the thousands, right? 5,000. It's now 2.3. Okay, you guys can't see this, so that probably made absolutely no sense. So here's our new, I'll show you what I did. I just reran these. So with a smaller sample, my test statistic is now 2.3 compared to 5,600. So it went down a lot. Well, I was going from 86,000 observations to 100, right? It's going to go down a lot. Now, with a smaller sample size, I still found a pretty similar R squared. In fact, if you look at the difference between the R squared and restricted and unrestricted, it's pretty similar. It's just now I found that from a smaller sample, so it's less reliable, right? That's kind of what dividing by that n minus k minus 1 factors in, is that if I found the same exact difference in R squared from a smaller sample size, it's less reliable because it's more likely it's driven by outliers. When I've got 86,000, a couple outliers isn't going to be driving those results. And so those are going to be a lot more reliable kind of differences in those R squared. So I can't reject at any of our kind of statistically significant levels. I can't say that adding in those two variables of age and whether or not no assistive equipment was allowed had any impact on the total weight lifted. Okay. Any questions on that before we keep going? Okay. Good. All right, so the next thing I want to go through. We can kind of ignore this for right now. Do I want to do this? No, I don't want to change topics yet. So I'm going to add in something else that I think is worth looking through with this data set. No, it makes no sense to change it. So I'm going to just copy and paste that exact same regression. We're going to just look at this like smaller sample size yet, because when we had 86,000 observations, to be honest, everything we do, the p-values are probably going to be what? 0, right? So let's just work with a smaller data set to really hammer these points home. So, oops, I can type. So what if I add in more restrictions, right? So I go back to the data. I don't have a ton of additional variables, but I do have kind of this weird one, which was, let me see, where's it at? Age squared. So this will kind of, we'll talk more about this after the exam. We'll dive into nonlinear relationships, but for the sake of now, we'll just think about we're adding in this additional variable, which is age squared. And then I'll also add in this category of wraps, right? So here I'll say age squared and wraps. Right? So I'm now going to run this regression, but I want to do a joint significant test. So it's the same sample size, same 100 observations. I'm running the exact same regression, except for now, I want to test the joint significance of all 4 of these variables. Right? So my unrestricted model, once again, is just using body weight and male. So I've now got 4 restrictions. So what's that going to do? I'll rewrite this out so it's easy for us to see. So here's our, and don't let me forget to show you the actual formula sheet after we get through this example that you'll have for the exam. I just want to make sure everyone knows where it's at in Canvas. It's been there for a while, but just in case that's something I haven't been able to find. So if I have, now I'm not playing around with differences in sample sizes, right? Now I'm comparing to that additional joint significance where I only looked at the joint significance of 2 variables. I now want to do the joint significance of not those 2, but those plus an additional 2 or 4. So what's happened to Q? Q is now 4, the number of restrictions I have will be higher. Now, what will happen to K as well? Yeah, it's gonna go up by 2, so K is gonna be a little bit higher as well. If Q goes up, what happens to this fraction? Goes down. If K goes up, what happens to my denominator? It's a little bit, well, I'm subtracting a larger value, so it's a little bit smaller, which means this whole fraction will actually be a little bit higher. What do both of these things do to my F statistic? Numerator's smaller, denominator's larger, my F statistic is going to be smaller, right? So when I add in this more restrictions, I'm gonna end up with a lower test statistic. At least for now. We'll throw a wrinkle into this in a second, but in general, we add in more restrictions, we would expect that F statistic to go down. And it kind of intuitively makes sense. You know, it's gonna be easier to say that two things, right? Because every time we add another variable, it's like we penalize ourselves for that. And so it's going to be easier to just say that 2 variables are good as opposed to 4, because every single other variable, I'm now penalizing myself again, right? That's kind of what that divided by Q is doing. It's not the most technical way of thinking about it, but that is what's happening. So I'm going to go to my regression. I'm going to run this unrestricted model that includes all 4 of these variables I want to test, as well as the original 2, right? I'm going to run this and see what happens to my test statistic. So I thought that it was going to be lower. It actually went up. So let's think about what, God damn it. Sorry, I shouldn't have said that. I mean, darn. So what's going to happen when I run here my unrestricted model? Oops, where is that? And I test all 4. Oh, now here. This is the one we had before. This is the one we have after, just so I can kind of get them, not too much of scrolling. So before we had an F stat of 2.3, now it's 4.7 almost, right? So why didn't it go down, right? So the effect of testing more restrictions, that effect will always pull your test statistic down. But as I'm adding in more variables, what could also be happening?
You're doing ones that are more.
I'm choosing variables that are better at explaining my Y variable. So in this case, these 2 variables I added in, how are they increasing my F statistic? Well, if I'm choosing really good variables, right, that are increasing that R squared, what's going to happen to that difference between my unrestricted and restricted model? It's now going to be larger, right? Because if I'm choosing, like, these variables, adding them in, it hurt me because I was adding in more restrictions. But if they're really good explanatory variables, they're going to increase the R squared by a lot, right? So that difference is going to go up. Also, if this goes up by a lot, what's happening when I do 1 minus that? This becomes a smaller value. So what effect is that having? Both of them are going to cause that F statistic to increase. Now it's like going back to, I don't know what all majors are. If you took 251 if you started in Kelly, or if you're 371 if you're pure econ. We had like simultaneous shifts in supply and demand. The answer was always indeterminate, or it depends, right? Same kind of thing here. We know that when we add in more restrictions, that's going to cause us to see a lower test statistic. But if they're really good at explaining that Y variable, they increase the R squared enough, we can kind of overcompensate for that, right? And so the answer here would be, what's going to happen if we do a test for a higher number of restrictions? Depends on what those restrictions are. If they're really good predictors, then they're going to overshadow that negative effect that's coming from adding in more restrictions. If they're really bad predictors and they don't increase R squared very much, well, you know, adding in the more restrictions, that's going to now be the one that kind of wins out. Okay. Any questions on that before we keep moving? And I'll try to bring in one. I'll hunt through my data sets to find one, because to be completely honest, for any variable that makes sense to include in your regression, usually it's going to win out, right? Usually, as long as you think this variable is going to have some effect, this will likely be the one that's larger, right? It's going to overshadow this effect of adding in more restrictions. But if you had somewhere you had some variables where it's like, this doesn't matter at all, then you could see that adding that as a restriction actually is gonna lead to a lower test statistic. So I'll try to find a data set where I've got some variables that like aren't related to the Y variable at all. So if we include that, hopefully we can kind of see evidence of the opposite, right? But the real answer is it depends, right? Crap. Any questions here before I keep moving? Does that make sense, hopefully? At least enough for now. We still got some class periods to work through a lot of this. All right. So where are we at? We got what? 30 minutes. How do I want to use this time? We'll revisit that. We started out with one. So I do kind of want to revisit this idea of dummy variables and excluding one. So I have these three different categories that the meat could be, right? So it's either raw, which was no assistive devices, wraps, minor assistive devices, multiply, the most assistive, right? So if I'm thinking about, if I try to run this regression, what's going to happen in Excel? Anytime it's a 1 here, what will the other two categories always be? So we have perfect multi-collinearity, right? I had someone ask me about this in my last section, and I don't think maybe I did the best job when I don't want to be hard on myself. I did a fine job explaining, but if there's something I didn't do that I think sometimes helps light bulb kind of click with people, right? So let's say I'm running this regression. Total kilograms lifted. And I've got an identifier for are you over 65? Okay, it's not what I'm. There we go. So this is going to be our regression, right? So you can think about it as x1 here is going to be are you over 65? Okay. Let's say I have a second variable in my data set. So instead of 3 categories, we're just going to have 2 to make this point. And let's say that second variable is are you 65 or younger, right? 2 dummy variables. Well, anytime I know that someone's over 65, what do I automatically know this variable is going to be equal to? If I'm over 65, how can 65 or younger be equal to anything other than 0, right? So they're direct linear functions of each other. So what I'm really thinking about, if I try to include this second variable into my regression, or kind of in general terms, well, this x1 variable, it's just going to be equal to 1 minus x2 in absolute terms. Anytime someone is 65 or younger, this should be a 0. Anytime someone is not 65 or younger, this should be a 1, right? In fact, I think the way I have it set up here, I don't even need this absolute value. So what could I do? I could plug in this equation, right? And really, when I'm including both of these variables, I'm really only including one variable, right? Because I don't really have 2 variables. Like this second variable gives me no additional information, right? If I know that they're over 65, yeah, I already know that they're not 65 or younger, right? So it provides me with no additional information. So when you try to run this regression and state it, it's like, I've got the same variable, so I've got now this coefficient, I'm trying to be adding. It's not coded to be able to display that to you, right? And in fact, the true effect would be like what? Beta 1 times negative x2 plus beta 2 times x2. So you'd have to actually do the math, but it doesn't fit the syntax of Stata, how it's going to run these regressions. In fact, it violates some matrix algebra procedures, and which is why it really can't do it. That's the real answer why it doesn't allow it to do it. But I think in more intuitive ways, well, if I have dummy variables that are direct linear functions of each other, knowing one, I automatically know the other. So including both my regression, I'm trying to put the same information in there twice. That doesn't make any sense. So we've got to leave one of these categories out. Excuse me. Any questions under this idea? Sometimes this will help kind of with this idea of multicollinearity. Now it becomes more complicated if we have more variables. So here we've got 3 categories. So we just need to make sure that we leave one out. So if I run this regression, one kind of nice thing in Stata is it tells me, I'm going to kick one out for you, right? I'm not going to allow you to do that. Okay. So another way I can think about these dummy variables now, this kind of categorical. So was it no assistive devices, minor assistive, the most assistive, right? What if I wanted the difference between this kind of raw and wraps category? From this regression, what would I do? So remember, how would I interpret these dummy variable coefficients? If the lifters or this, meat, the lifter is occurring in a raw meat with no assisted devices, we would predict the total weight lifted is 113 kilograms less than our omitted group, the one that was using this multiply assisted device, right? So it's always going to be how much lower this category is relative to the one you left out. So if I want to know what's the difference between these 2 categories, what would I do? Huh? So I could rerun the regression, leave one of them out. If I just have these results though, it's just going to be the difference between the 2. So why? So let's think about what these dummy variable coefficients are telling us. So here I've got 207. So if I'm making predictions and I'm just thinking about where's the intercept for these different groups. So if all the variables here are equal to 0, male, age, and body weight, where would the intercept be for multiply? Well, if it's a multiply meet, both of these variables would be equal to 0. 0 times this plus 0 times this doesn't get added to our predictions. The only thing that would be in our prediction is this constant. So if I'm thinking about what that looks like, let's say I was thinking about total kilograms lifted and the relationship between kind of body weight. And I wanted to know when body weight was equal to 0, where does that multiply category start out? Well, we just said it's simply the intercept coefficient. I think it was like 207, right? So this was kind of our omitted group, which was multiply, right? We then had the second group was if they could use wraps, right? So if we go back and look at that slope coefficient, and I won't switch back and forth, I'm just going to look at it here. The coefficient was negative 109. So what that's telling us, if I make predictions for someone who's in one of these meets that they can use wraps, it'll not only have the intercept of 207, but it's also going to have this additional coefficient, which is negative 109, right? So that would put me at what? 90, wait, what's it? Negative 109, so 98, if I'm doing my math in my head correct there, right? So its intercept is going to be significantly lower. It starts out at a low, and that makes sense. If I can use less assistive devices in that category, the starting kind of predicted total weight lifted will be much lower. And then the raw category would be the intercept plus the coefficient on that raw category. I think that was negative 113. So I've got additional what? So this would be 94, I think would be its starting point, right? So when I have these categorical dummy variables, those coefficients, so the excluded group, it'll just start out wherever the intercept is. The included groups will start out wherever the intercept was, plus whatever the slope coefficient was on that dummy variable. Okay? So it's kind of starting like a different starting point for each one of these groups. Okay? And then as body weight goes up, we would almost have like, watch is getting in the way. I almost have like 3 lines of best fit, right? Other questions on this before we keep moving? I think if there's anything else I want to say here. I think that's it. Any questions? Okay. So. Go back here. All right. So, which one of these categories makes the most sense? This is kind of just revisiting an old question, but I think maybe you didn't ask it. Generally want to keep out the lowest or the highest, right? That usually makes the most. But even if we don't, we can compare any two groups, to your point, we can just look at the difference in the coefficients. We already talked about this in an earlier example. So I'm not gonna hammer this again. This is what I think I just did this a little bit out of order. I just wanted to make the point that when we're dealing with these really large sample sizes, this was where we said, oh, where are they at? Every p-value is 0. Smaller sample sizes, some of those p-values start to get high and we fail to reject now. So we already kind of worked through an example there, so we don't have to worry about that part of the code. Don't have to worry about this. We already talked about sample size differences. So I think this could be worth thinking through, all right? So let's say I have another omitted variable example, right? Just to kind of get more practice at this. Well, where we at in time? And we'll use this one. There's another good one I have in the practice exam that we can use. So let's just do a really simple one. So let's say I run this really basic regression, which is total weight lifted and the individual's body weight, right? So I got this here, 5.2. Let's say I have this important omitted variable of age, right? So without running that regression with age in it, what do we think the sign of that bias is that we're seeing in this estimate of 5.2? Okay, so, well, cool, didn't switch over yet. This is a good time to also point out, you go to the Files tab, and actually, I think I put it on the homepage as well. Yeah, you got the formula sheet right here. It's under the Files tab as well. You can kind of click on it. It's also a good time for me to bring this up, and a couple people I've gotten emails throughout the semester, and I've already addressed this with them. Okay, well, we'll do it through the file so I can actually show this. Here we go, formula sheet. So if you try to open up a file, we'll open up this formula sheet file. Yeah.
It says that it hasn't been published yet.
Did I not edit? That might explain why it's taking forever. Oh, I did. Thank you for saying something. So there, okay. Now we should hopefully be able to access this. Let's see. I'll do it through the files. So it might take a second. We'll wait for it to load. But sometimes if you try to view PDFs or even Word documents or different files on like a web browser, like opening it up from Canvas like this, it'll sometimes display to you as like, just looks like things are messed up. Like things will be like overlapping, it shouldn't, they'll be kind of in the wrong places. I don't know why this is taking so long to open here. But I wanted to show you that sometimes it can occur, so it depends on, here we go. Depends on your device here. I don't have any compatibility issues. All the equations are showing up okay. But if you had a certain device and you're using a specific web browser, maybe some of this is like garbled and doesn't look right. What's probably always a safe bet for any file in this class is instead of viewing it on Canvas in a web browser, just going to download it, right? Download the actual file and open it up in the program. That'll 99.99% of the time resolve any compatibility issues. But if you're trying to view these files like on a web browser page, sometimes there's some weird compatibility issues there. So just out of practice, I would always download files and open them as opposed to trying to look at them through Canvas. I don't work on Canvas, so I can't fix those issues.
Also for the exam, do we have to print out the formula sheet or what elements get them?
No. I'll bring every exam will have a formula sheet inside of it. Yeah. Yeah, and if you need Z or T table, which you shouldn't, anything that you would need, I'll have printed out in the exam. Yep. You should need, this is kind of, I'll go over this as we get closer to it. You should need yourself, a calculator, something to write with. Yep, I'll bring extra paper, I'll bring all that. All right, so we have that formula sheet, which kind of tells me, where's it at? Here's this equation, and now everything's not going to be labeled. So even though you have a formula sheet, maybe one good thing if you're studying, maybe print this out and like, maybe even before you even dive into that practice exam, write out what every formula kind of means. And then, you know, if you're studying enough with it, even though it doesn't have it on the exam, you can kind of imagine, or what I always used to do, like a quick cheat. It's not cheating, but it's kind of, right? Like if I know what they are ahead of time, as soon as I get that exam, I pull that formula sheet out, and the ones that I always couldn't remember when I was studying, I write those down right away, right? I mean, that's just a good, it's not cheating, it's just a good thing to do, right? These are the ones I can't remember. I'm just gonna use these very few, I'm gonna make sure I know going in, I look at it right before I put everything away. I got the formula sheet, okay, I'm gonna write those down right away, all right? So I don't forget what those formulas represent, okay? So this one, this last one, and I'm gonna give you the exact same form. It's gonna be in the same order, so I'm not gonna try to trick you up, right? That'd be pretty mean. I could do that, but I'm not going to. So here we have kind of this form that tells us here's the bias that exists, right? So we're gonna write that out and think about when I see this estimate, and I was just running total kilograms lifted, body weight in kilograms, right? And I was thinking about, I omitted this important variable, which was age. So I wasn't including age in my regression, right? Those results that we were looking at. So we said the other part of the bias will be the covariance between body weight, the variable I included, the variable I excluded, divided by the variance of the variable I included, right? So this is going to be my bias, okay? So what's the sign of that bias going to be? Well, this is where if I ask you on an exam, I'd probably leave this open-ended. So if I ask you for the sign of the bias, it's going to be like a short answer, right? And then as long as you justify the different components of that bias, I would grade it accordingly. Now, if I gave you some additional output, like where I told you that, you know, some state output where you could find the covariance, I give you the regression not of the naive one where you left it out, but once you included it, we talked at the beginning of class, you could then calculate the size, right? So that could be a multiple choice or something where I'm looking for a very specific answer. But here, if I'm just asking you for the sign, you just have to justify and kind of give an explanation as to why you know what these things are, right? So what does this represent? Well, it would have been the effect that age had if I'd included in my regression on my Y variable. So you guys haven't probably felt this effect yet, but what happens to your body as you get older? It deteriorates, right? So you are continuously getting like, that's actually just like some cell, like your cells are literally always like deteriorating throughout your entire life, right? So as you get older, right, we're thinking about not going from like 5 to 6 or 6 to 8, right? We're thinking about adults, right? So progressing, if it helps to think about going from being 20 to 30, 30 to 40, 40 to 50. What do you think is probably the effect of age on any physical activity? Yeah, are 50-year-olds running marathons at faster times than 25-year-olds? No, right? I mean, there may be one, right? But on average, as you get older, what's happening to physical performance? It's decreasing, right? If I did include age in that regression, any type of physical performance that I'm measuring is probably going to have a negative impact on it. So I've got a negative sign here. The variance on body weight, well, variances will always be positive, right? We're taking the difference between the y minus the average y and squaring it. Anytime you square something, it's positive. The covariance between body weight and age, as someone gets older, in general, what happens to your body weight? Once again, you guys probably haven't experienced this, but it's harder to stay small, right? So as people get older, they tend to weigh more, right? So what would the sign of this bias be? Negative times a positive divided by a positive. The estimate we're seeing is probably going to be too low, right? So we saw 5.2. The actual estimate is going to be something that's probably larger. So we can, in fact, see if that's the case because we have the data. So my old naive regression, instead, I'm going to now include age here, we would expect the new estimate we see, if the old one was a little bit too small, right, had a negative bias in it, when we remove that bias, now we should see a slightly higher estimate. Sure enough, not much higher, but instead of 5.2, 5.277. And if we wanted to, we could actually come up with, well, what's the size of that bias? So let's say instead, I didn't give you this output, and I just gave you this output. And then I also told you, I'll save it in the command here. Correlate body weight with age and give me the covariance. So let's say instead, I gave you this regression output as well as this. And I said, if you run a naive regression where you leave out, age, what's the bias going to be? Well, we said the bias is going to be the effect of that variable we omitted, so negative 2.05, right? So if I'm thinking about here, negative 2.05 was that slope coefficient, times the covariance between the variable we omitted and the variable we included. Well, when we talked about the naive regression, we excluded age, so the covariance between age and body weight would be 18.85 approximately. The variance we divide by the variance of the variable included in our naive regression. So if we left out age, the variable we were including was body weight. So we said these covariance matrices, the cross or the diagonal, tells us, well, the covariance of something with itself is just the variance. So we had the variance of body weight was 524.4. If I copy this, paste it into Excel, I get about negative 0.07. So the size of our bias was about negative 0.07. Well, I can verify this, like on the exam, I would just give you this. But if I looked at the actual naive regression, what estimate did I see? 5.2. What was the actual coefficient if I included age? 5.27. How much lower was it? 0.07. That bias was negative 0.07. Okay. So, I can ask you different variants of this question, kind of thinking about just what the sign would be if I gave you the naive regression, or I give you the non-unnaive regression, as well as the covariance information, and ask you what's the size of the bias. Those are two likely types of questions I would ask you on the exam. And I wrote the exam, so I might have a little bit of insight information. Okay. Any questions over anything there? Okay. Excuse me. So, what do we have? 7 minutes. And I can already see, I'll probably get this file updated. So if you download it, re-download it after 3 o'clock today. I'm missing parentheses here for, well, I probably was just going quickly. But I'll make sure that I kind of fix that. I don't like the fact that those aren't there. But if you go to the main page here, current things that we have. So we've now kind of started looking through this exam review. You've still got, where is it at? There they are. The sample questions for that quiz that's not due until what? The 11th is going to be the end of the day, Friday this week. So you've got the rest of the week to think about still taking that third quiz. That problem set isn't due until we start class next Tuesday, right? So give you a little bit extra time to kind of work on that. Still got office hours on Wednesday. We come by office hours on Monday. I'll probably, let me make sure before I tell you this. I try not to schedule things. Yeah, I should be here Friday as well. So if you do have a time you want to stop by Friday, just shoot me an email. I can kind of make sure I'm in my office. But I want you to do well. So start, take that third quiz seriously. That'll be good kind of preparation for the exam. Those quiz questions sometimes are a little bit more difficult even than exam questions. Now they're more often than not multiple choice. And so in that sense, they're not going to give you as accurate of a representation of what short answer questions will look like. I would review those quizzes, especially the ones you got wrong going up into the exam. That practice exam is also going to be really a good thing to review. I tried to make it pretty representative of what you'll see on the exam. I would also, it sounds weird, but I would then kind of, I did those two things. I'd go back through the problem sets. And so this is why I wanted to have that problem set due a little bit earlier in the week. Because as soon as that due date passes, I'm going to get the solutions out there. So I'll get the solutions up to all the problem sets so you can start to review those. I was trying to hold back on those because there were some issues with people not understanding about uploading due files. And so I want to make sure the problem sets 1 and 2 get graded before I put solutions out there. That should be fine. You'll kind of have those. I would go back and review, not the part where I'm asking you to code or create variables. That part shouldn't matter for the exam. I'm not going to ask you any coding questions or how would you create this variable. What I might ask you is so problem set 1, probably not a lot on there because that was mainly just coding and Stata. 2 and 3, I start to ask you a little bit more why. Or like there was the one on problem set 2, right, where I said find A, B, C, D, E, and then I don't know if there's an act, but whatever it was. Well, that's like a little bit more worked through problem that you weren't actually doing. So things like that would also be good kind of study, right, to go back and review those problems leading into the exam. And then just attend class the next 2 class periods. We're just going to be working through more examples, just trying to give us better understandings. I might say it slightly differently one day, and that topic or that type of question will make a lot more sense, right? So hearing things more ways, it's just increasing the probability that one of those ways connects with you, right? I'm more likely to reject the null that didn't make any sense to. Okay, so any questions from me? We're out a little bit early, so feel free to ask me after class. Otherwise, I'll be in my office tomorrow for office hours. I will see you guys on Thursday.